Hejsan allihopa och vart välkomna ska ni vara till dagens event här på Goto 10. Innan vi drar igång så vill jag passa på att berätta lite om Goto 10 för alla er som är nya medlemmar har idag. Goto 10 är en kostnadsfri mötesplats som drivs av Internetstiftelsen. Internetstiftelsen är en oberoende organisation som verkar för ett internet som bidrar positivt till människan och samhället. Communityt här på Goto 10 bygger på att våra medlemmar stöttar varandra och delar med sig av sina erfarenheter för att växa och utvecklas tillsammans. Här på Goto 10 kan du delta i event som är skapade av andra fantastiska medlemmar, precis som du gör idag. Men du kan också sitta här och jobba i vår arbetslunch. Du kan spela in poddar, du kan använda våra 3D-skrivare eller så kan du anordna ett eget event om du vill. Och allt det här är helt kostnadsfritt. Jag hoppas att dagens event blir värdefullt för dig. Om du vill dela med dig av din kunskap eller har några frågor, kontakta oss gärna på Goto 10.
Hej allihopa! Välkommen hit. Går det bra på svenska? Ja. Kul! Marie heter jag. Jag sitter som projektledare på Syntronic som bor i huset bredvid. Planen för idag är att Jakob kommer hålla en kort presentation om oss på Syntronic och bilprojektet som vi har. Och sen helt enkelt är det dags att köra lite bil, så den som är sugen får jättegärna prova. Härligt! Då kör vi!
Yes, so I'll do this presentation in English. Syntronic began here in Sweden, but then we moved to multiple countries around the world, and it's a global design house today. We do hardware and software. And if you have more questions, you can talk to Niklas here. Okay, so today we're going to talk about the Herbie project we've been working on. It's an autonomous vehicle project, and we develop it to explore and test new technologies, among other things. We have both this hardware platform and a simulator platform that, or I guess, the project is designed to work in both platforms and environments. So, given that, we can compare the results because the simulator obviously has very good data in terms of sensors. It's ground truth, more or less. So when you compare it with the real world, with all the complications that come from that, we can see the limitations that we maybe didn't discover in the simulator, and then go from there. So it is a work in progress. We've recently made many changes as well. So, for example, the motors are recently changed, and we're gonna drive a bit slower today than we are used to. So I'll do a slight overview here. We have a platform launcher where you can set the choice essentially. And we designed the project to be plug and play more or less to the specified platform you chose. And we have AutoSAR standard applied as well. So the platform launcher launches the different systems needed for the project. So we launch a visualization package, a SLAM toolbox. We launch a path planner and a vehicle control, among other packages that help communicate over the system. And we use ROS2, and it communicates over Wi-Fi. So the Piker platform, we chose it specifically to be pretty cheap and be challenging, essentially. So this map is pretty challenging for the system we have. The LiDAR has a minimum range of 10 centimeters, which is quite tough. It's recommended minimum range is 10 centimeters. It is challenging in this map. And the vehicle dynamics with the servo we have in this is also quite challenging. You essentially need to max turn most of the turns to make it around. So this causes us to be challenged with all the algorithms we use and really understand the methods we are applying. So yeah, when we went from the simulator and made this map and started using the hardware platform, obviously there's a lot of difficulties that arise when you have a real-time system, and Yeah. It arises because we had several issues. Like we realized we had too low voltage because we initially had 2 batteries, and we had some sync issues as well with because ROS2 is over Wi-Fi. We had to realize what message goes where, and in the simulator it was not as problematic. And we found multiple issues like this, and it's interesting to see the difficulties that can arise when we go to our real world. So yeah, we get new perspectives on the algorithms we have that we thought were working well in the simulator, and all the limitations that come from the real world we learned a lot from. So yeah, and we also changed the chassis recently, and internals and stuff. So yeah, some differences in vehicle dynamics actually, because how you connect the servers and this. Which also affects the challenge of the map we have. The processing is split between the RPI on the car and a laptop. So we will be running it on this laptop here in the demo later. So we're also using the simulator on the other side, and it's open source. It's based on Unreal Engine 4. And we made custom maps and vehicles inside this map and this tool. And we made a same scale map as this to really compare the results we see in the real world and what like in space, how much can we turn and these things, and see when the sensors are correct or ground truth more or less in the simulator, how do we perform there, and we can compare these kind of things there. And it was pretty fun to detect some issues when we just we made a model in CAD, and then did animations in Blender, and then exported it to Carla. And it's interesting how the physics can work if you don't assign everything correctly. The first attempt was just the car flying around because the physics were not correctly set, and it's an interesting process. So I thought to show a small video here of the simulator and the visualization of the SLAM. Yeah. So we have 2 maps here. We have the local grid map that is centering on the car and following wherever it goes, and then we have a static global grid that we defined beforehand how big it is, which is the current state of what we're working with. We're not dynamically changing the map. We're not dynamically changing the size of the map, I would say. Right. So yeah. Okay. Yeah, so to make the map and understand the environment, we're using SLAM. And SLAM involves localizing the car, and it needs the sensors, the sensibility to do that. So we use extended Kalman filter here. And then we do sensor fusion. So we have a wheel encoder on the car that essentially finds how long, like a small distance that the car has traveled. And then we use the IMU to detect if there's a rotation happening. And then we fuse the 2 data and send it to the SLAM. And then it combines it with the LiDAR data to make the map. So this small GIF here is just the pose estimation we have while the car is running. Yeah. And per path planning, we're using Hybrid Star. It's a rather simple algorithm, and preferably, from our experiences, we didn't want to do like too strict of a collision avoidance, because if you do, for example, if you do a line of sight and follow the track like the path we have, you can forcefully remove paths that are too close to walls. Which could be good, but then if you end up too close to the wall due to like control error or following it and then wanting to make a new route, then you would remove it forcefully. So then like doing the algorithm just penalizing being too close to the wall is a more smooth solution, is what we found. But you need some strictly. Obviously, you don't want to run into the walls, so it's a balancing act. So finally, I just want to talk generally about some experiences in this project. So as I said, this map was quite challenging for the system, just in terms of turning and making a path that's easy to follow, or like manageable to follow. Because as soon as you make a slight mistake, you need to max turn more or less all the time. And having a very precise relationship between the car and the map we created is required. We had some issues initially when we made the first iteration of the platform. We had issues with the voltage we found. We added 2 batteries and it should be fine, but it was kind of over the edge of what we could power with that. And then it has like these hard, difficult issues where the hardware kind of random issues. You drop the voltage but then go up again, and you don't really know exactly why the performance is going up and down and like, changing. So these kind of issues are interesting to find. And initially, we just we glued 4 magnets onto the wheel and made a wheel encoder with a Hall effect sensor, and just to again challenge what we can do with the lowest amount of technology. But it was clearly too low resolution for us. We needed timing issues as well with the IMU for the extended Kalman filter. But it was interesting, and now we changed to motors which have way more resolution, which is required for good localization. So, and ROS2, we found some issues with signal timings and real-time timings for all the, especially SLAM, and the localization needed really precise updating. Yeah, because of multiple of these issues, like we saw some drift in the post estimation due to voltage drops because we missed messages and this kind of stuff. And many issues, like going to hardware can be very challenging. But yeah, that was the short introduction of what we're working on right now. Do you have any questions? Okay. Let's go to the demo then. Yeah.
So, like, I understood the presentation correctly. You used these encoders to count the number of turns and position of the wheels.
Yeah, a specific distance between the magnets on the wheel. So initially we had only 4 magnets, so 4 ticks, you could say, between for each revolution of the wheel.
Yeah, exactly. And then you you calculate some kind of average from all of the wheels to get this kind of plot in some way.
Yeah, the extended Kalman filter does this sensor fusion. So the IMU is actually the one like detecting forces on the car and detecting if it's rotating or something, and the wheel encoder is only detecting the movement forward. So then we sensor fusion to detect like the path or the curve that the car is taking.
That's cool.
Yeah.
Thank you.
Any more questions? Okay, then we'll go ahead with the demo. We'll keep the stream going if anyone online has any questions. But the presentation part is done, so let's do some driving.
What do you see? Transistors on a chip? Or a complex landscape of engineering perfection with the potential to make the world a slightly better place? It's all about perspective. We are an engineering design house, a global team of experienced engineers in the forefront of technical development, global, yet always close by your side. We provide hardware and software solutions, embedded systems, and wireless applications around the world. Our customers use these solutions to save lives and to connect people, industry,